Just tell a story. Actually, is this working? Can you hear me? No? Yes? I've got no idea actually what's happening. This is my band's Facebook page, MetaX. So we're a live coding band. So we hacked the Overtone, which is the system I'm working on, live in front of audiences. Here's us playing at Wising Arts Festival. The more recent one's pretty cool. Where is this one? So that's at a so-called Algo Rave. Okay, Algo Rave. Which is about live coders creating music for people to dance to. Actually, at this gig, people were actually dancing. And a couple of ladies came up afterwards and went, "Man, that was sick," which I think is a positive sign. And yeah, you can see what we're doing here is actually writing live in the moment, making sounds, looking at the audience. So the algorithm is write some code, make some sound, look at the audience. Are they dancing? No, change the code. Are they dancing? No, change the code. Are they dancing? Yep, keep it with that. So like you have to be able to be live in the moment, to be able to reflect on what's happening in the audience context, and to be able to come up with imagine new ideas and to make sure that you can actually realize those pretty quickly. And I guess that's the theme of what I'm trying to talk for the rest of the time is about that essence, so that the feeling of what it is like to be coding live, what tools you might need to actually enable that, and what it kind of allows you to do as a human, in terms of your creativity. And I think that Lisps fundamentally are systems which actually allow this. Really, they focus on this kind of environment, and Clojure is no exception to that. Now, some cool stuff I want to focus on in terms of the functionality of the functional aspects of this, but really, if there's one takeaway sort of point I want to get across already is that sort of from a Christopher Alexander perspective, being in the moment, being able to explore what it's like to be inside of the code, I think is a key element. So it's not just necessarily the ability to ahead of time plan the structure, the topology of the code, to be able to understand its relationships with each other, maybe even to make some sort of formal reasoning about this, which is, I think is in essence of a lot of this conference. Just the ability to be inside the code, to look around, to be able to have the time to look around, and then the ability to make modifications live, and to hear, in this case here, or maybe visualize, or perceive in some way, I think is really the essence of what I'm trying to get across. So I think, and really the tools I'm making are about that nature. And I think that I'm completely sidetracking here, but I'm doing it sort of purposefully, because this is the feeling I've got from the entire conference, is that I think focusing on software development and tools from an engineering perspective is really interesting. And we have sort of Dijkstra to blame for that, for inventing the term software engineering at that NATO meeting all those years ago. But I think that actually that's only one element of programming. I think that being able to be in the moment, to explore it, I think is a really powerful way of programming. And that's what I'm going to show you now. So this is me doing that. So actually, if you really want to get a full experience of what it's like, what I'm trying to explain, it's really hard for me to do that in 20 minutes when I'm sort of in front of you with the microphone talking. You need to come to one of these algorithms. Okay, so we're going to play in Seabase and Berlin in a month's time. We're going to play in Lithuania. We're going to play in Belgium. If you want us to come to America, if you want to ship us out, we'll come play for you. So, right, so I've worked on a system called Overtone. Has anyone here heard of Overtone? Oh, awesome, right, we're already started. Okay, so let's try and create a blank space. Clojure mode. So what Overtone provides is it's a Lisp environment. It sits on top of something called SuperCollider. So SuperCollider is pretty much the most powerful synthesis engine available today that's open source and is programmable. So the essence is that the interface to the system is a programming interface. And so the author of SuperCollider, James McCartney, he made an explicit move to separate what he called the synthesis engine from the language used to control this. And that move was to allow people to explore other languages to actually interface with the SuperCollider synthesis engine. And so what we've done is exactly that. So we've taken the Clojure programming language and we've interfaced it with the SuperCollider synthesis engine. And so Overtone is essentially no more than a fancy front end of SuperCollider. So a lot of the stuff you're hearing, the good stuff isn't about Overtone, it's actually about SuperCollider. It's pretty awesome. And there's language interfaces for all sorts of other languages of SuperCollider as well. So I can move this way. So in Clojure, one of the things you do is you create a namespace. We call this one eggs with a lot of G's for fun. I'm going to pull in Overtone. And now I have a full programming environment. So I can sort of demonstrate sign oscillator. Look at that, sign oscillator, pretty quick. So again, this is what I'm trying to talk about, this sense of being in the code. I can write something. Is that big enough? Shall I make it bigger? Is that better? Yeah, you like that? Can you get on the camera? I'm not sure. So very quickly you can write some code and you can hear some results. And actually, I'm going to digress slightly again. The notion of being able to have this very fast feedback cycle from having an idea to hearing sound is, I think, is fundamental. And if I have time at the end, I'll talk about how this applies to education as well. But so here we are, write some stuff. That's all we can do is sine waves, so that's pretty cool. Actually, all you need is sine waves because you make out all the sounds from sine waves. But we can do different frequencies. That's very low, noise next door. Or we can do saw waves, they're pretty horrible to hear. Raspy saw waves. They get pretty cool if you sort of have two saw waves slightly off frequency, so they interpolate, a bit like when you drop two stones in a puddle, the waves sort of interleave. It's that interleaving, which is pretty interesting. You can hear that sort of going in and out of phase, pretty cool. And you can start to build up these synthesizers like this. I can pass that through a low pass filter, say 2000 Hertz. You can see it's sort of taking off the higher order frequencies. And this is nothing special or exciting necessarily. You've probably seen this kind of thing before. And if you haven't, it's amazing. So the people I show this to, they're like, what? This is ridiculous. If you've seen it before, then it's not that exciting. But essentially we have an environment where, well, this is an Emacs, but you can use any closure environment, where you can actually write some code and you can hear some results straight away. Cool thing is that this is and there's a lot of technology going on behind the scenes as well to make this happen. So this S expression describes a design for synthesizer, which when I evaluate the code, gets compiled down to a binary format, which represents the synthesis and the synthesizer itself, or the design of it. That then is shipped to SuperCollider, which stores it, and then separately we then trigger it for 5 seconds and then kill it off again. So all that stuff's happening just by evaluating that form. But we can see actually what's happening here. So if I turn that into a synthesizer, def synth, if I can type, give it a name, foo, all good names. Synth, yeah, exactly, thank you very much. I can then call it like a function, and you can't hear a thing. So this is actually indicating some magic which is happening. The magic which is happening is this actually is running on SuperCollider server. Now we'll stop it, and you can all hear it stopped. What's actually happening is that the demo is adding some extra things. It's adding this out UGen, which basically puts it to the speakers. So it allows you to sort of ignore doing that. So we can hear this again. This is going to play forever. And so we can see here actually there's a bunch of stuff that's happening. It's like having a live environment where you could actually talk to it allows you to do things like pop-up documentation like this. This isn't statically put it aside. It's not. There's no files with all these documentation in. This is actually Emacs talking directly to the closure process, saying, "Hey, you just typed it out in this namespace. Are there any symbols which you can find? Yep. And do you have any doc strings? Yep. And I'm going to format it for you." So I can actually create new functions and get the doc strings to appear immediately, which is absolutely beautiful. And so there's no necessary to compile something. I mean, it is when I execute it, it is compiled, but I don't have to do some static ahead of time compilation and some munging of namespaces and strings. It's just there because the environment allows me to live introspect. And so I can also start to see things because this is just a data structure. I can say show graph is synth, and I can show you what it looks like actually in sort of Maximus P style. So you can see actually there's two saw waves being piped into two low pass filters, which are then put to this magic out UGen. Each of these boxes are so-called UGen, which is Max Matthews' term for unit generator. In fact, it's interesting how synthesis hasn't changed, since it was invented pretty much. He was drawing diagrams like this in the 60s. And the out UGen represents the speakers. So there we go. The cool thing is that we don't have to stop there. Does this make sense? You with this so far? Cool. So, what's going on here? Go away. Oh, gosh, yeah, I might do that a bit. That was an image of all the spaceships, actually, in all science fiction. Yes? Oh, yes. Oh, this is fancy pantsy. This is pretty cool. This is a feature we've... So, Overtone's like the Borg. Thank you very much. So the question is, how on earth were the two low-pass filters in the diagram version when I've only written one LPF symbol in the text? Is that correct? Was that the question? Yep. So Overtone's like the Borg. So when we see a good feature, we suck it in. This is something called multi-channel expansion. So if I pass, SAW is only expecting typically one parameter, in this case the frequency. So if I pass a vector of 2 parameters, it sees that and it actually expands that out to 2 saw waves. And anything else below that in the tree also gets expanded out. So it's a very quick way for me to actually create multiple channels of things by just specifying the multiplicity in one place. And it just spreads out everywhere. Yeah, and that's available in SuperCollider language. It's a really nice feature. So what we can do is, in the actual definition of the synthesizer, we can actually start to use functional stuff. So let's try and think about. I've got some. Before that, I can show you a bit more complicated one. So here we have a snippet which generated me a pluck string synthesizer. Hopefully that's not killing next door. So you can see here actually we can start to even make more interesting synthesizers pretty quickly. So here we're using white noise and we're mixing it in with this pluck UGen and we're distorting it and we're passing it through some filters. And we can start to see what that looks like. See, some things are getting a bit more complex now. The nice thing here is that this diagram illustrates all the sort of the complicated things that are happening. So you've got the stuff in grey, stuff in white, and stuff in black. The grey means something is actually at audio rate. The white means at a control rate, so it just doesn't get executed as quickly. It's just for efficiency. But the black ones, they're the cool things. They're the things you can control. So when you trigger the thing, you can specify new values. But also when it's executing, you can modify it on the fly. And let's have a look at what that means. So if I pull in... I also have a bunch of really cool music sort of abstractions. So here I can actually not call C5 as a function, but just a keyword. I can say note C5, and you can see at the bottom in Emacs tradition. Obviously, it's not. This is really dreadful for presentations. I can actually print it here. So you can see here when I call note C5, it just gives me the MIDI notes. This is nice to work with, and this is pretty cool. So this is when we go to as programmers, we go into new domains. So I worked in the pharmaceutical industry for a little bit, and you go and you learn the domain and then you program something that actually would work for them. Music is no different, and so I had no idea what notes were and scales were and arpeggios and chords. You know, I had a rough idea. So I sat with a friend for a weekend and who really does know these things, and told him to explain them to me, and he did, and I programmed them out. And so this namespace here is the result of that. So I can see now if I forget what a note is or forget what a chord is or a scale, I can go and look at this code. And it means that if anyone else wants to learn Overtone or know what these things are, it's actually a pretty good way of getting into music theory. At least the very simple elements of music theory. And there's, yeah, and it's just really a very simple way of describing these elements. So the same way I can do notes, I can do scales. So C4 major. That returns me a list of all the notes in the scale, and I can do something like for each of those elements. Each note in that scale, play the pluck string of that note. Ooh, that's all at the same time, so that's not necessarily very nice. So I can sleep for a little bit between them. Again, that's quite nice, and I gave this talk to a bunch of schools, and I was giving them computer science talks, but for some reason one of them wanted me to talk about music to musicians. When I said actually going to talk about computer science, they were about to leave. But when I was doing this, to actually sort of understood why this is interesting, because we can really start to get to the core of what they want to teach in a very interactive way. And again, you can look at what actually scales are, and you can see that this is the function which defines scales, and we've got different degrees, and even up here you can start to see that I've implemented them by a lot of them putting just the intervals, but some of them where I can see some patterns. Now let's work on that. Like for example, this case here, the Ionian sequence is often rotated around for the Ionian, Major, Dorian, Phrygian, Lydian, all sort of stuff. So you can see here, I write a little function and I can actually rotate it around. So this is nothing to do with efficiency at all. This is nothing to do with anything other than trying to communicate to people reading the code what's going on here. So it's trying to communicate the patterns internally, which I think is really important. So what am I doing now? Going back to eggs. So the thing is, you can do this kind of stuff, but you can also there's other ways of actually communicating with this code. So I can, instead of just doing a straightforward iteration with some sleep, I can do what's called a temporal recursion. So this comes back to Andrew Sorensen and in Promptu is a system he's worked with. And this is a really nice way of creating structures which go through time. And so what you do is you create a function, like this, called my loop or something, and that can take some parameters. So if we take time as a parameter, some notes as a parameter, and a separation time, and in there we can do a bunch of stuff. So we can say at the time, do something. So we're going to let's introduce the sample piano. It's quite nice. Overtone.synth.samples piano. So this is just like the pluck string. So it just plays a sample piano. And this is another nice thing as well. One of the core goals of Overtone is to try and make this kind of programming, this kind of environment, more accessible to more people. So we're not trying to be hidden like magicians. And so we want to make sure that everything's open source, including all the samples. So the sample piano is actually hosted on something called freesound.org. And we got that on there. So there was a really nice, I can't remember who recorded them, but he released them all sort of open source on his website. And so we actually got them onto the freesound so that we could actually pull them down. And when those samples are available, it's a very simple way to actually suck them down to Overtone by just writing the number actually of the sample. Anyway, I can play the sample piano, and I can take the first of the notes, and then so that's going to play me the first note of the notes I'm going to play. And then this is the idea of temporal recursion: is you call yourself, but not in the way that consumes a stack. So it's not recursion in the normal sense. It's guarded by time. So I'm actually scheduling myself to be called in the future. So I'm going to use apply to call myself, but I'm not going to use the standard apply. I'm going to call something called apply by, which applies at a specific time, actually ahead of a specific time. So what I want to do actually is I want to create this new time. The new time is the summation of the time and the separation time. So if I've got a time to do something and I've got the separation time, I can calculate when the next thing to do is by just adding these things together. So apply by the new time. You can see here, the arguments at the bottom, I've taken the second's time, but I also take a function to apply. So I'm going to call myself my loop, and then I'm going to pass some parameters: the new time, the rest of the notes, and the separation time. So now I can call this thing. So my loop t. Let's make some notes. Score. Oh, that's too big. Unfortunate. Pictures. I made this thing, but I can't remember what it is now. Degrees. Actually, I'll just steal it from you. Here's one I wrote earlier. So here's just a simple way you can actually start to represent notes in terms of Roman numerals. So here are the degrees, and I can turn them into pitches by passing them to a diatonic C4 scale. So here I just have now a bunch of MIDI notes and nils for rests. And so I could actually call this thing. So if I call my loop T with the pitches and 200 milliseconds, so T is a time, so it needs to be now. Oh, so it's doing something, but then I'm breaking. It's breaking because it's trying to play a rest, and that doesn't work. And this is crucial as well. That if I've got something that goes wrong, I don't want it to kill my entire system. So, but I should be allowed to have errors. Having broken code is really important, actually, in this kind of environment. So I don't want necessarily anything to guard me from making broken code. I want to be able to make broken code, and I want to be able to see what goes wrong, and I want to be able to fix it live without things really blowing up in a really terrible way. So what I'm doing here is I'm actually playing all the notes. And what I should actually be doing is saying when first notes. So when it actually exists. Oh, Dominic Orchard is in the room tweeting. Thank you very much, Dominic. When first of notes. Let's try this again. We are great. That's played it now for us. And what I can do now is I can get that to play forever by just cycling the pitches. So this is about using infinite sequences and using the infinite sequences to feed into this temporal recursion. This will play forever, and it's using Super Collider to do the timing, so it really is super accurate. So that's quite nice. And so people were doing Steve Reich phrase patterns. It's super easy to do that with this, because now we have this means to actually play a sequence super accurately. We can just call two of them. So if I let the time to be some slightly point in the future, so to make sure that we can schedule it now. So let's add 200 milliseconds from now. Let's call my loop twice with the time t and 200 hertz and 203 hertz. 200 hertz. 200 milliseconds between each node. You can hear actually both things sound at the same time, but very quickly they'll diverge. You can listen to that for ages, but we're running out of time. I've also got, you can do crazy things like this. Look at this. So, and people like this because it actually is fairly credible because you're making some interesting sounds. Typically when you hear people do this academic stuff, it's always the MIDI piano. That's not so exciting. So dubstep's much better. Where did that go? Oh, I lost it. There we are. And the cool thing about this, a couple of cool things, sounds cool, but also it was written by somebody else in another language which I was able to translate to Overtone. So this is the beautiful thing about writing these synthesis techniques in a formal sort of language. It allows you to translate it and understand the internals of it. And so we can actually evaluate it like this, but I can control it now. That's louder, quieter, is that too quiet, too loud? So because I can look at, you can see the, I've got these different control parameters here. So wobble's a pretty cool one. That's what you want with wobble dubstep. Wobble. Yes. So you can have a lot of fun with this just by triggering these things. Oh, actually, it has a different rate as well. Control. Yeah, the crowd goes crazy. So, yeah, and I mean I can go into more detail on this, but I'm running out of time. And so what I'm really trying to express is that having a system which really allows you to manipulate these things quickly and to be able to make mistakes, to treat it like a canvas where you can just throw things on it and not worry too much about the formal specifics of it, and just use it as a place to actually experiment and play, actually is really important. And as a final thing, I'll end with, let's see if I can find it now. What was it called? So here's here's me translating Extatis Gnossium number 1 into Overtone language. So as we sort of have a sneak, there's the spaceships. That's all spaceships in science fiction. It's amazing. Anyway, where did it go? Oh, I didn't have it here somewhere. Just the spaceships, isn't it? Well, I thought I had it. I thought I brought it up. It was just, anyway, it was a score for Extatis Gnossium number 1. Anyway, I read it and I found patterns in it, so I was able to find different phrases. And then I was then able to then concatenate those phrases using sort of standard techniques. So all the notes on the right hand are as the concatenation of these things. All the notes on the left hand, the concatenation of these things. It's all large font, so it doesn't look so good. And this is all different pitches. Here I'm putting to A flat major. And the cool thing here is that there's only 2 bits of state, where I am in the left hand and where I am in the right hand. And the rest is there. And so I can, if I evaluate this, just by calling this function, I'm getting all the right-hand notes. It's not very loud. And the left-hand notes. And I can reset it. And then the cool thing is I can just assign it to my piano, so I don't use my piano normally, but by pressing the same note, I just get the next notes. He's enjoying it by doing this, which I think means turn it down. So I can reset it, and I can play the piece, and then I can say goodbye. So this works. Reset the positions. And the nice thing is that one of the things I wanted to be able to do with Overtone is be able to play with my eyes shut, so I'll see if I can do the eyes shut. There you are, thank you very much. Yeah, thank you very much. The majority. So the question is, when I'm repeating the questions, okay? Oh, right. So the question was, when I have a gig, to what extent am I writing the code live, or is it pre-prepared? And for me, I mean, this is an interesting philosophical question for live coders. I mean, some of them like to go and have a blank slate. But I mean, to be honest, is there a blank slate? I mean, you would have libraries, or you've written your own language. So some live coders have written their own language, which is really terse, like regular expressions. And they can make some crazy sounds by just putting a very simple snippet of text up there. I like to just have most of it prepared. So the thing is, it's not about writing a lot of code. It's about being able to improvise and to move around between things. And so there's two different aspects. One is the aspect of to what extent is the performance prepared, and to what extent is the performance reproducible by other people. And so what I'd like to have is have lots of the structure there, but I want to be able to play around with it. And I don't think it's so much, for me, it's not so much of an importance of being able to do it all from scratch, but it's to be able to, in a moment, feel, am I putting my own soul into what I'm doing? And the answer is most of the time no, and it's trying to find better ways of doing that more. And so really it's a selfish goal of I want to be able to control it more about how I feel right now. So that's an answer. So there's going to be a combination of code written and code performed, and yeah, the code is typically a starting point. And actually, between gigs, often we'll snapshot what we're doing, put it on GitHub, so you can see what was the code at the start or the end of that performance. Yeah, question? So the question was two things. There's an assertion of the importance of the interactive language environment, and then the question of to what extent would a GUI not facilitate a similar kind of experience. Is that a fair thing to say? So, I mean, I bought one of these things called a Mono, which I forgot to bring, which was actually a nice device. It's a box of buttons, which is a grid. And this is way back when I started doing these things. And I bought this thing called MaxMSP, which is a GUI kind of environmental language. And I was starting, because this is where all the people using this thing were building their tools with this. And it had two massive issues for me. One was, well, actually lots. One was that the code was completely unreadable. So once you get to any level of sophistication, I didn't show you this actually, but when I generate the graphics of a synth-def, if I make a sophisticated synth sound, that thing is crazy complex. So trying to write that manually is just a nightmare. How do you debug these things? How do you write tests for them? And so this is, and what are the abstractions? I can't have max patches which take max patches and pass them down through max patches. I want to be able to do that. And so GUIs, I think that when you look at MaxMSP, it's got great tutorials for getting started. It's beautiful. Things look simple. But when you get to any level of sophistication, and you need to very quickly, for me, they don't handle the abstraction in an elegant way. So languages, I think, are currently what I see as the best way to interact with these things. Does that answer your question? So the question is how is the synthesizer element implemented? And the answer to that is that the way we do it in Overtone is that the def synth is a macro which takes a sort of a body which itself is a set of functions, and we apply all those functions. And those functions, the result of those functions is a data structure. And so we ended up with a nested set of data structures. And so we end up with a tree essentially, which is just a immutable tree, which we then have a function which takes the parameter and spits out a binary, which then we send to supercompiler. Which is why I can draw it with GraphViz, because I take that compiled immutable tree and render it to GraphViz. Question? One more. The question is, what happens with runtime errors? I love them. They come up and I say, yes, something's gone wrong. It depends entirely. So if you don't, the runtime error semantics of Clojure is that of the JVM, and so if there's an exception, then it blows up. So it's up to the programmer to catch these exceptions. So if I have a run loop, for example, I have a drawing tool called Quill, which I didn't show, which is pretty nice. So I can take any element of the synthesizer tree and draw it. So, for example, I could take the wobble of the dubstep bass and make a circle wobble the same rate. But in that draw loop, if I have an exception, then I automatically catch that in the quill environment. And then I also throttle the execution so it slows down. It gives me a chance to fix it, and when it fixes it, it comes back up again. So I have to be able to tolerate these kind of changes, and that's very important. Sorry? During a live performance, absolutely. Yeah, I try to minimize that, of course, but when there is an error, I don't want it to stop the music. Yeah. Thank you.